Introduction to Dynamical Systems. Part 5. Analyzing stability of fixed points in the two-dimensional case. As follows from the title of this lecture, we are going to consider the stability of fixed points in two-dimensional dynamical systems. First of all, let us write down the general form of an autonomous dimensional system on the phase plane. The general equations for such a system read as shown on the slide. As usual, we assume that the velocity vector components f1 and f2 are represented by some smooth functions of x1 and x2. We need to find the fixed point, and to do this, we set the functions f1 and f2 to 0 simultaneously. Then, suppose we found the fixed point by solving this system of algebraic equations, and we need to expand the functions f1 and f2 in Taylor series by analogy with what we did before. The expansion for the function f1 reads as is shown on the slide. The first term represents the value of f1 at the fixed point. By the definition of the fixed point, we know that this term must be equal to 0, because it represents the first component of the phase velocity vector at the fixed point. The expansion contains two linear terms which include deviations from the fixed point x1 minus x1 star and x2 minus x2 star, and it contains higher order nonlinear terms. If we assume that the deviations from the fixed point are small, then we can neglect the higher order terms, and also with account of the zero value for the function f1 at the fixed point, we end up with a linear approximation of the function f1 close to the fixed point. We can do the same for the second component of the velocity vector, f2. Next, we need to introduce small deviations from the fixed point. The components of the deviation vector are z1 and z2. z1 is the difference between x1 and x1 star, and z2 is the difference between x2 and x2 star. The mathematical condition of smallness for both z1 and z2 is expressed as pointing out that the moduli of both z1 and z2 are much less than 1. Next, we need to rewrite the original equation for the dynamical system. Instead of writing it in terms of x1 and x2, we need to rewrite it in terms of z1 and z2. We find the time derivative of z1 by differentiating the difference between x1 and x1 star. In doing so, we point out that the time derivative of x1 star is 0, so z1 dot and appears to be equal to x1 dot, which in its turn is equal to f1. Next, we replace f1 by its Taylor expansion, in which we neglected all higher order terms, like what we did in the previous slide. This gives us the expression for z1 dot, in which we denote x1 minus x1 star as z1 and x2 minus x2 star as z2. Finally, we obtain the linearized equation for the small deviation, for the first component of the small deviation from the fixed point z1. In this equation, both partial derivatives are taken at the fixed point, and we can obtain a very similar expression for the second component of the phase velocity z2. This allows us to write down a system of the so-called linearized equations, which describe two ordinary differential equations of the first order for the components of the deviation vector from the fixed point. The system of linearized equations can be rewritten in matrix form as follows. In the left-hand side, we write down a vector consisting of the time derivatives of the values of z1 and z2, and this is equated to the product of a certain matrix and the vector of deviations with components z1 and z2 itself. The matrix in question consists of the elements which are equal to the partial derivatives of functions f1 and f2 which are taken at the fixed point. This matrix is called linearization matrix or the Jacobian, and we denote it by the bold capital letter J. We can now rewrite this equation with account of the new notation for the Jacobian. Please remember that because in the Jacobian the values of all derivatives are taken at the fixed point, the components of the matrix J are all constants. Linearized equations are linear ordinary differential equations with fixed coefficients, and we can solve them analytically. The solutions to linearized equation read as follows. Namely, both z1 and z2 appear to be combinations of some exponents. The numbers lambda 1 and lambda 2 in the exponents represent the eigenvalues of linearization matrix J. Now, lambda 1 and lambda 2 can be real, but they could also be complex. More precisely, they could be complex conjugate. The stability of the fixed point, which we're analyzing, will be determined by the temporal behavior of the functions z1 and z2. The temporal behavior of the small deviations z1 and z2 will be determined by the actual values of the eigenvalues lambda 1 and lambda 2. Therefore, the stability of the fixed point in question will depend on these values. If the eigenvalues are complex conjugate, they can be represented in the following form. Lambda 1 or 2 is equal to the real part of the eigenvalue, which we denote here as u, plus minus the imaginary unity I, which is equal to the square root of minus 1, multiplied by some number w. We substitute this expression into the expressions for the deviations, and we start from the first deviation, and that's what we obtain. We can see that this is a combination of some exponents to the complex arguments. Represent each of these exponents as the product of two different exponents. Start from the first exponent. This exponent can be represented as a product of an exponent to ut, which is a real function of time, and an exponent of iwt, which is a complex function of time. Equivalently, the second exponent is the product of an exponent of ut and an exponent to minus iwt. Each of the exponents to the complex arguments can be represented using Euler formula as a combination of a cosine and a sine. Let's do it. In particular, the first exponent to iwt is the sum of cosine Wt plus I sine Wt, and the second exponent can be represented by analogy. We observe that in this expression there is a common factor exponent to ut. Let us take this factor outside the bracket and obtain this expression. We observe that inside the bracket we collected terms with a common factor cosine and the terms with a common factor sine. Now cosine is multiplied by a sum k1 plus k2. Because k1 and k2 are just some constants, we can denote this sum as some other constant c1. And similarly, ik1 minus ik2 is just a constant, which we can denote as c2. With account of these new notations for the constants, let us rewrite the expression for z1 of t. You can see that this expression has the form of two periodically oscillating terms, cosine of Wt and sine of Wt, and these terms are fluctuating with the same frequency, angular frequency w. The fluctuating terms are both multiplied by the exponential function, and if u, the real part of the eigenvalue, is positive, then this exponent grows in time indefinitely, so the deviation z1 grows in time while fluctuating. And if u appears to be negative, then z1 will be decaying in time and fluctuating at the same time. By analogy, we can obtain an expression for z2, which is the second component of the deviation vector, and it will have a similar form. Let us briefly summarize what we have learned so far. Although the original dynamical system was nonlinear and its solution could not be found analytically, we can linearize this system near the fixed point and obtain a system of linear equations, which are solvable exactly. To solve a system of linearized equations, we in fact need to find the values of eigenvalues of the linearization matrix, or of the Jacobian, as we called it. These are some constants, and these constants can be real or complex conjugate, and the values of these constants will tell us how the phase trajectory will behave if we set initial conditions quite close to the fixed point. And if the eigenvalues, for example, are complex conjugate, the phase trajectory will fluctuate, will oscillate with a certain frequency around the fixed point. And depending on the value of the real part of the eigenvalue, the phase trajectory will either go away from the fixed point if the real part is positive, or it will approach the fixed point if the real part is negative. And if both eigenvalues are real, then depending on their exact values, we will find more about the stability of the fixed point. Fixed points on the phase plane can have different types of stability, and in what follows we are going to classify fixed points on the phase plane based on their stability. To do this, it might be slightly easier if we introduce two additional quantities. Namely, if we look at the Jacobian matrix, linearization matrix, for this matrix we can introduce a determinant delta and trace tau. Start from the determinant. The determinant can be calculated as follows. df1 by dx1 times df2 times by dx2, that's the product of the elements on the main diagonal, minus the product of the elements on the other diagonal, namely df2 by dx1 times df1 by dx2. Now, from linear algebra we know that a determinant of a matrix is equal to the product of its eigenvalues, and that's what we write. Now look at the trace. The trace of the Jacobian is simply the sum of the elements on its main diagonal, namely df1 by dx1 plus df2 by dx2, and again from linear algebra we know that the trace of a matrix is equal to the sum of its eigenvalues. In what follows, we are going to consider the determinant, and we will look at various values this determinant can take and at various opportunities for the stability of the fixed point. Start from the case when the determinant delta is negative. This can only mean, since the product of lambda 1 and lambda 2 is equal to this determinant, this must mean that the eigenvalues are real, and if one of them is positive, the other must be negative, so they must have opposite signs. In that case, the fixed point will be called a saddle, and the saddle fixed point, which in this picture is shown as the empty circle, it is an intersection of two curves on the phase plane, which are called invariant manifolds. A saddle point is an intersection of a stable manifold and an unstable manifold. A stable manifold has arrows which go towards the fixed point in this picture, and the unstable manifold has arrows which go away from the fixed point. If we set initial conditions exactly on the stable manifold, we are going to stay on this manifold forever as time goes by, and we are going to gradually approach the fixed point but never reach it exactly. If we set initial conditions on the unstable manifold, again we are going to stay on this manifold forever as time goes by, but we are going to go away from the fixed point. Now if we set initial conditions at some small distance from the fixed point, and suppose we start close to the stable manifold in the upper part of this figure. Initially, the phase trajectory will loosely follow the stable manifold, and thus it will be approaching the fixed point. When it will approach the fixed point closely enough, then it will start feeling the influence from the unstable manifold, and it will turn and it will start following the unstable manifold. So overall, the phase trajectory that started nearby the fixed point will ultimately go away from this fixed point. So the saddle fixed point is not really stable. Now consider the second possibility for the determinant. Suppose the determinant is now positive. Given that it is the product of two eigenvalues, lambda 1 and lambda 2, we can have two cases. First of all, the eigenvalues can be real, and if so, they can be either both positive or both negative, so they must have the same sign. In that case, the fixed point is called a node. And here we have two cases. Suppose both eigenvalues are positive. In that case, the small deviations will monotonously increase in time, and they will not fluctuate. In that case, the phase trajectory, which starts close to the fixed point, gradually goes away from it. Therefore, this fixed point is unstable. Consider the second possibility when both eigenvalues are negative. In that case, the fixed point is a stable node. And if you remember the expression for the small deviations will be monotonously decreasing in time. And that means that the phase trajectory will be monotonously approaching the fixed point. So this is a stable fixed point. Consider the second option for the determinant to be positive. It is possible for the eigenvalues to be complex and in particular complex conjugate. So they can be represented as real part u plus minus I, imaginary unity, times the imaginary part w. The first possibility is when u, the real part, is positive. In that case, the fixed point is called unstable focus. The small deviations from the fixed point will be fluctuating, oscillating with a certain frequency, and the amplitude of the small deviation will be growing in time. That means that the phase trajectory which starts close to the fixed point will be spiraling around the fixed point and gradually going away from it. So this is an unstable fixed point. When the real part of the eigenvalue is negative, our fixed point is a stable focus. The small deviations will oscillate with a certain frequency, and their amplitude will be decaying in time. It means that the phase trajectory starting nearby the fixed point will be gradually approaching the fixed point while making spirals around it. And the third possibility is when the real part of the eigenvalue is 0. In that case, the small deviations fluctuate with a certain frequency and a constant amplitude. In that case, a phase trajectory which starts close to the fixed point will neither go away from it nor approach the fixed point, and the spirals will continue forever. Such a fixed point is called a center. To summarize, there are 6 types of a fixed point on the phase plane with different stability properties. Let us consider how to analyze stability of the fixed points in an example of a two-dimensional dynamical system. The example we're going to consider is the famous van der Pol oscillator, which we know very well already. In this representation of van der Pol oscillator, we have 2 phase variables, x and y, and the right-hand sides we denote as functions f and g. We already know that the van der Pol oscillator has a single fixed point at the origin with coordinates 0 and 0. To analyze stability of this fixed point, we need to form the Jacobian, and in order to do that, we need to find partial derivatives of the functions f and g at the fixed point. So find these derivatives as follows. First of all, look at the function f. This function does not depend on x, so its partial derivative with respect to x is equal to 0. Next, we need to differentiate function f with respect to y. Because the function is simply equal to y, its derivative with respect to y is 1. Look at function g and find its derivative with respect to x. In doing so, we assume that y is simply a constant, a number. So we differentiate the first term with respect to x and obtain minus 2 epsilon y multiplied by the derivative of x squared, which is 2x. The second term is a constant multiplied by x, so its derivative with respect to x is just this constant, which is equal to minus omega naught squared. Finally, the derivative of g with respect to y can be found as follows. The second term in g does not depend on y at all, so its derivative is 0, and only the first term depends on y. And if we differentiate it, we obtain epsilon multiplied by the bracket 1 minus x squared. These derivatives allow us to form the Jacobian matrix as follows, in which we substitute the values of these derivatives into their positions. We need to find the values of the derivatives at the fixed point at 0, 0. The first row contains the constants, so it stays as it is, and only the second row in the Jacobian depends on x and y. Consider the second row the first element. This element has two terms. In the first term, we substitute x, y equal to 0, and this term disappears, so we are left with minus omega naught squared, which is a constant, so this looks correct. Then in the second row, consider the second element. We substitute the value of x equals to 0, and we are left with epsilon times 1, which is equal to epsilon here. And the Jacobian is finally formed, and it has 4 elements, all of which are constants. Once we obtained the linearization matrix, we can find its eigenvalues. To remind you, the problem of eigenvalues is stated as follows. We assume that there is a certain column vector x, which is called an eigenvector. And we need to form the following equation. We take matrix J and we multiply it by the column vector x. The result will be another column vector. And this product should be equal to the product of vector x and a certain number, lambda. Here x is called an eigenvector and lambda is called an eigenvalue, which we need to find. So how can we find lambda? Look at the left-hand side of this equation. We know that if we take vector x and multiply it by the identity matrix I, nothing will change. To remind you, the identity matrix I is a matrix, a square matrix, which has the diagonal on which we can put only ones. So the diagonal elements of this matrix are equal to 1, and all other elements of this matrix are equal to 0. So identity matrix multiplied by x gives us x. So the right-hand side does not change if we perform this multiplication. Next, we formally move all terms of this equation to one side, to the left in our case. We notice that x is a common factor, and we can take x outside the bracket, like this, and we bear in mind that x was in the right, to the right of everything from the beginning, and it must stay to the right. It would not be appropriate to move it to the left. Otherwise, we would make a mistake. The equation we obtained is a matrix equation in which the unknown is vector x. Because J is known, I is known, lambda is number, which we hope to find, and x is a vector consisting of some unknown elements. From linear algebra, we know that the solution for x exists only if the determinant of the matrix in brackets is equal to 0. Now, to ensure that the solution for x exists, we need to ensure that this determinant is indeed equal to 0. And this can only happen if lambda takes appropriate values. So let us first of all find this determinant, and to do this, let us write out the linearization matrix J and the identity matrix I multiplied by the number lambda. By performing matrix operation of subtraction, we end up with a single matrix whose determinant we need to find. The determinant of this matrix is the product of its diagonal elements, elements on its main diagonal, minus the product of the elements on its another diagonal. Namely, we multiply minus lambda by epsilon minus lambda and subtract minus omega naught squared multiplied by 1. Because we subtract a negative number, the resultant term will have a positive, will be equal to plus omega naught squared. And this has to be equal to 0. The expression which involves lambda is called a characteristic polynomial, and we obtain an equation in which a characteristic polynomial is set to 0. This equation is algebraic equation of the second order. It's a quadratic equation, and we can solve it, hopefully with ease. And as a result, we will find two eigenvalues, lambda 1 and lambda 2. Depending on the values of parameters epsilon and omega naught, these eigenvalues could be real or could be complex conjugate. Now consider all possible values that our eigenvalues can take. In this slide, in the top, I rewrite the expression for eigenvalues. Consider the first case. Suppose the expression under the square root is positive, and that means that the square root itself is going to be a real number. Then epsilon is a real number, and we need to add or to subtract from it another real number. This means that both eigenvalues are going to be real. In that case, the respective fixed point is going to be a node. Stable or unstable, we will find out. If it is a node, it means that the phase trajectory that starts near the fixed point does not oscillate, and it will not be spiraling around the fixed point, so it will be going towards the fixed point or away from it in a non-oscillating manner. Consider the first subcase. Suppose epsilon is negative, and to form the first eigenvalue lambda 1, we need to take epsilon and subtract the square root of epsilon squared minus 4 omega naught squared. Because epsilon is negative, the square root is real and negative, so two negative numbers added together will give us another negative number. So the first eigenvalue is negative here. What about the second eigenvalue? To form the second eigenvalue, if you look at the formula at the top of this slide, we need to take epsilon and to add the square root. Now epsilon is a negative number, but the square root is a positive number. And the sum of a negative number and a positive number can be either negative or positive. So the sign of the second eigenvalue is not that obvious immediately. So let us investigate in more detail. Consider the expression under the square root. Here we have epsilon squared, which is a positive number, from which another positive number is subtracted. It means that this difference is less than epsilon squared itself. If we take a square root of both sides of this inequality, in the left-hand side we have the square root appearing in the expression for the eigenvalues, and in the right-hand side we have the magnitude of epsilon. And this inequality tells us that the square root is less than the magnitude of epsilon. And if we form the second eigenvalue lambda 2, what we have is that we have a negative number epsilon, to which we add a positive number which is smaller than epsilon. And overall we will obtain a negative number. So the second eigenvalue is going to be negative 2. Our conclusion is that our node is stable, and the picture qualitatively depicting the phase trajectories around the fixed point is shown here. Now consider the second subcase of the same case. Assume that epsilon is now a positive number and start from the second eigenvalue, because you will see it will be more obvious. To form the second eigenvalue, we take a positive number epsilon and add a positive number square root. The result is another positive number, which means the second eigenvalue is positive. What about the first eigenvalue? If you look at the formula at the top of this slide, to form the first eigenvalue, we need to take epsilon, which is positive, and to subtract the square root, which is positive. A difference between two positive numbers can be positive or negative, so it is not obvious. And by analogy, what we did in the previous slide, consider the expression under the square root and deduce that it is less than epsilon squared, which means that the square root itself is less than epsilon. Now to form lambda 1, we take a positive epsilon and subtract from it a number which is less than epsilon and positive. The result is going to be a positive number, which means the first eigenvalue is positive. So in this case we have two positive eigenvalues. We already know that the fixed point is a node, and our node is going to be unstable. The picture illustrating the behavior of phase trajectories around this fixed point is shown here. Now consider the second case, in which we assume that the expression under the square root in the expression for eigenvalues is a negative number. In that case, eigenvalues are complex, and moreover they are complex conjugate. In this case, the fixed point will be a focus, and the phase trajectory will be oscillating, spiraling around the fixed point. The focus can be stable or unstable, so let us investigate further. Consider subcase 2.1, in which we assume that epsilon is a negative number. Look at the expression for eigenvalues. The expression under the square root, epsilon squared minus 4 omega naught squared, is a negative number, which means that the same expression multiplied by -1 will be a positive number. So let us represent the expression under the square root as a product of -1 and another expression plus 4 omega naught squared minus epsilon squared. This will allow us to rewrite our eigenvalues as follows. We have a fraction. In the upper part we have epsilon plus minus the product of the square root of -1, which is imaginary unity, written as I, and of the square root of some positive number. And this is divided by 2. Now we have singled out the real part of our complex conjugate eigenvalues, which in our case is epsilon over 2. And since epsilon is negative, the real part is -2. We know that the small deviation from the fixed point will be fluctuating at a certain frequency, and its amplitude will be monotonously decreasing with time. And this means that the phase trajectory, which starts nearby the fixed point, will be spiraling around the fixed point and converging to the fixed point with the course of time. This makes our fixed point a stable focus. Now consider the second subcase, in which we assume that epsilon is a positive number. As we showed in the previous slide, epsilon over 2 appears to be the real part of complex conjugate eigenvalues. And the real part of complex conjugate eigenvalues shows how small deviation from the fixed point fluctuates around the fixed point, if it is going to increase or decrease in time. Since epsilon is positive, the real part of eigenvalues is positive, and the small deviations fluctuate and grow in time. This means that the phase trajectory is spiraling around the fixed point, and at the same time it is departing away from the fixed point. And our fixed point appears to be an unstable focus. To summarize, our analysis of stability of a single fixed point in the van der Pol equation revealed that depending on the values of parameters epsilon and omega naught, the fixed point can have different stability features. It can be stable or unstable, and it can be a focus or a node. I would like to acknowledge professional and technical assistance from Olga Sosnovtseva and Dmitry Pasnov.